Hello everyone, this will be your exam 3 solutions video. Before I get started on the solutions video, I will go ahead and tell you that there were a couple of ambiguous questions I think on the exam. Also maybe I think there was like one mistake in grading in one of the questions. So I've decided already to give everyone a 16-point curve on the exam just to account for those ambiguous questions and the one mistake I think is on the that happened during the grading when Blackboard graded the exam. So let's go ahead and get started. So the first question is what type of bond cleavage does the following reaction involve? We've got a cation there, and I forgot to change it to making comments here, drawings. Let me do that real quick. Okay, so we have a cation there, and we have an anion there. That means that a electron pair was went with the bromine, right? So that would definitely be a heterolytic bond cleavage. Next, which of the following? Oh, sorry. Predict the sign of the delta S, which is entropy, for the following. Whenever you go from a straight molecule like that, open molecule like that, into a cycle, right? You have less degrees of freedom for each of the atoms and the bonds. So that means that you actually have gone from more disordered to less disordered, right? And so that means you have a negative delta H. Delta S. Give the following rate law for the order of this reaction with respect to MEI, right? So methyl iodide. Which is funny because that says MEL in there, mel. But so that's a typo on the exam. Anyway, each one of these concentration units here have 1 as their exponent, so this would be a first order reaction with respect to MEI or methyl iodide. What is the effect of a catalyst on the reaction? On a reaction, it increases the rate. That's D. And then which arrows indicate a nucleophile or nucleophilic sites? Well, you have electrons there on the nitrogen, so that can be a nucleophile, and you also have the lone pairs of electrons up there on the carbonyl oxygen. So the answer there would be B and C. All right, let's keep going here. Which of the following is the most stable carbocation, right? We already know that is the tertiary carbocation is the most stable, so that's structure 3. Let's see here. What is wrong with the mechanism shown? Excuse me. The only thing wrong with the mechanism shown here is that we don't have an arrow to kick off that leaving group right there. So that would be C. The arrow should be removing a proton from... No, that's not right. I read that one wrong. It should be this one. B. An arrow is needed to indicate the loss of the leaving group. Yeah. Sorry. That's a mistake I made here on the solutions video, not a mistake in the grading of the exam. Okay, so yeah, B. Me reading the answer choices too fast, I guess. Next one is what is wrong with this mechanism? That's really weird. Why is that happening right there? Right? That's just really weird. There shouldn't be any arrows coming from that carbon right there. So in fact the arrow should be going like this. So what letter is that? Let's see, I think it's C. The arrow indicating the formation of the carbon-bromine bond. Nucleophilic attack should start at the bromide ion. Yes, so that's C. So this one identified the appropriate error for the equation below. So this is just asking whether or not this will be a reversible reaction, a forward reaction, or a reverse reaction only, right? Or no reaction at all. Well, in fact, this will be a forward reaction only. And the reason why is because I told you to remember this. One of the things I said on in the lecture, right? It was, instead of having carbon dioxide here, CO2, right, which is the gas that was being expelled in the reaction was nitrogen gas, if you remember, right? And remember that whenever you have a reaction where one of the products is a gas and it can just float away, then it can't be a reversible reaction. Okay, it can't be a reversible reaction because one of the products is gone now, right? So in this case, CO2 is definitely a gas. Okay, definitely a gas, and so the reaction definitely cannot proceed backwards if the CO2 has floated away. Okay, which of the following is a nucleophile, electrophile, and leaving group? The hexoxide here is the nucleophile. The alkene is the electrophile. So that's like 2-bromo propene, and then the leaving group is the bromine. So where is that one at? Nucleophile is cyclohexoxide. Electrophile is bromo-2-propene, and then leaving group is bromine. Yeah, so that's B. That answer is B. Okay, so this is one of the ones where I think that the question was graded incorrectly on the exam. It asks you the following name of the IUPAC name shown. We already know that it's going to be a 2-fluorobutane, but it has a chiral carbon, right? So it has to be RS configuration. And when you do this, right, we already know that the fluoride or the fluorine up here is 1, okay? And then we have a hydrogen in the back that is 4, right? So now you got to decide which one is 2 and 3. So on this carbon here, this carbon is connected to 3 H's. And this carbon over here is connected to an H, a C, an H, and an H, right? So that means that this carbon over here takes priority because it's connected to a carbon. This one is not, right? So this is 2, and this is 3, right? So just forget about the 4 because you know it's in the back already. You can just count 1, 2, 3, 1, 2, 3, like that. And then so that looks like it's going counterclockwise to me. Right? That looks like it's going counterclockwise. And whenever you're counterclockwise, you have an S structure. Right? You have an S structure. So that would be C. And I believe when this was graded on Blackboard, it said the answer was D. But it's not D because R is clockwise and S is counterclockwise. So that's one of the problems where I gave you back points for it, part of that 16 points added back. Okay. This one here, which of the choices is a mechanism for an SN2 reaction? Let's see here. SN2 reaction. Well, here we have a leaving group just leaving on its own, so that's an E. And I don't even know what that is doing right there. That's just wrong. And I also don't know what it's doing there. Right? So the only one left is C. This guy right here. That's the only correct mechanism. Next, which of the choices below is the transition state for this thingy here, right? Well, that's definitely not a transition state, and that's not a transition state. So the only thing, because that's actually missing some stuff in there. So the only thing you have now in between is structures 2 and 3. And so what you need to decide is which bonds are breaking and which bonds are forming, and it's definitely not the bond between the ethyl group here and the carbon, because the ethyl group is not the leaving group. What's the leaving group? It's the bromine, right? So here we have bromine as a leaving group. Here we have, cyanide as the nucleophile. So the answer to that one is 2. Structure 2. Okay, you discovered that the energy of activation for an SN2 reaction decreases when you change a solvent. What most likely is the reason for this finding? So remember that if it's an SN2 reaction, you want to have an aprotic solvent so that you can make the energy of the nucleophile higher, right? Because a protic solvent will actually stabilize the nucleophile, right? Because it can do hydrogen bonding. So what happened here is that what happened here, since that you have lower energy, your reaction decreases, right? That means you probably had it in a polar protic solvent. So the answer there would probably be C. Yes, C. You have substituted your polar protic solvent. Wait a second. You discovered that in the energy of an activation. Oh yeah, that's right. Let's see. See, I always get confused again, right? Because it's so this A right here and this A right here is so close. So they look like they're almost exactly the same thing on B and C. But that's right. You discovered that the activation energy for an SN2 reaction decreases when you change the solvent. So you used to have a polar protic solvent, right? And that's what stabilized your nucleophile, but you substitute it for a polar aprotic solvent, and that's why you have a lower activation energy right now, because it increased the energy, the potential energy of the nucleophile, so that it shrinks the activation energy between the nucleophile and the threshold is to actually do the nucleophilic attack. So yes, this would be C. Got to read those things very carefully. Almost second guessed myself. Let's see here. Next one. Okay. So, which of the following structures is the structure? Which of the following structures are made a product of the given elimination here? So, what we have here is a streamlined base, right? So, if it's an elimination reaction, we're going to be pulling off one of these protons right here. Okay. And so the base comes over, pulls off the proton, brings down the double bond, and we lose the chloride leaving group. Okay. And so the answer to that one would be this one right here. Yes. Structure 1. Right there. Remember, because if it's a slender base, right, or a streamlined base, not a bulky base, it can go through and pull off a proton from a least substituted. No, sorry, not least substituted. A more substituted? Yeah, from a more substituted carbon. If this were a bulky base like terp-butoxide, it would have pulled off a proton from over here, right, and then you would have gotten 2 as your answer, but it's not 2. This is methoxide. Methoxide's a very streamlined base. Okay. This was the difference between a Zitzev product and a Hoffman product, if you recall. Which of the structures below? Which of the structures shown is the most reactive in E2 reaction? The one that causes the one that results in a tertiary halide, right? So tertiary halide is the one that's going to be most reactive towards E2. So that's structure 3. Okay, what are the products for this reaction here? This SN1 reaction. So what's going to happen is we'll have the bromine leave as a bromide, and it gives you this structure here. like that. And then the SH can come over and do an attack there, or an attack back there, right? Because the bromine has left. So what that means then is that you'll either get a structure that looks like this, where we have SH coming out at you and the methyl group going in, or we'll have another structure that looks like this, where the SH is going behind you or going towards the paper, and the methyl group is retained its stereochemistry, or its configuration rather, and it's coming out. The methyl group is coming out at you. So let's see which structure has that. Definitely can't be that. You can't have two things coming out at you at the same time. You definitely can't be that because you can't have two things going backwards at the same time. I don't know why you would have a double bond at all when you're doing a substitution reaction. So yes, this I didn't draw it exactly the same way they drew it, right? But it's this one, structure 1. Actually, I did draw it the exact same way they drew it. Yeah, so structure 1 is the answer to number 17. Okay, next question is here. So this is a very similar question to the previous question, right? Which is a major product found for this reaction? It can't be any of these right here, because you can't have a positive oxygen and be a final product. But since this is an SN1 reaction, right, where you're substituting an OH for the bromine, the same thing that happened in the last reaction can happen in this one, where you get the attack on either side, and so it could be both 2 and 3. So that would be answer D. Okay. Next one, which of the compounds shown will undergo a rearrangement in SN1 reaction? The only one that would do a rearrangement would be structure 2 here, and the reason why it can is because it has a hydrogen right there. And so when we do an SN1 reaction and we lose this chlorine, right, we lose that chlorine as a chloride leaving group, we can do a hydride shift like that. And when we do the hydride shift, we end up with a tertiary carbocation, right? And a tertiary carbocation is more stable than what this was going to be, which is a secondary carbocation, so the answer is 2. Next. Okay, so this is another one of those questions about what's the error in the mechanism here. The error in this mechanism, before even looking at the answers, is that this right here, this part right here, there's nothing making that proton go away, so that that bond can come down and form the double bond. So whenever you have a dehydration reaction like this, right, water can come over and act as the base. And take out that proton like that, and then you have the double bond being formed. So, which one is that one? Looks like it's going to be D. Water needs to be added to the H bonded to the third structure so that the electrons from that bond can move to form the double bond on the upper right hand side. So the answer there would be D. Next. So this is another dehydration reaction. What is the error in the structure in the mechanism below? So let me scroll down a little further here because that's just their thing there. Okay, there we go. What is wrong with this one here? Okay, that's what's wrong with this one here. Once the oxygen up here deprotonates that proton, right, you've got to move those electrons over to the hydrogen sulfite, right? So that's what's missing, this arrow right here. And so that would be C. There is a missing arrow that should show movement of electrons from the proton, the bond between the proton and SO2 and SO3H. Yeah, that one, C. C is the answer there. Next question, we have another dehydration reaction here. And so, because we lost the OH. So, let's see here. Quite literally what can happen here is you can deprotonate, just like in the last reaction, right? Deprotonate just like you did in the last reaction. So that gives you, I'll draw it small down here. Okay. Okay, that's what you get there. And you also get a HSO4. Alright, this is... Okay. And then you can lose this you can lose this leaving group as a water, right? And then this HSO4 can come over, or even a water. That water that you just lost up there can come over and take this proton here, and this comes up here, right? Because there's the formation of carbocation right there, making a double bond. Okay, so this is actually one of those ambiguous questions that I was talking about here. I think that answer could either be 4 or 3, because I specifically told you in lecture that the alkene that was the most sterically hindered, the least sterically hindered alkene would be the one that would be most favored, but you always get a mixture of the two, right? But the problem is that you don't have any answer choices that will give you a mixture of the two, right? Or also the other problem is that it says what's the major organic product. And then the key, right, when Blackboard graded this, it said that it was going to be this structure here. And to me, I think that this structure right here, structure 3, I think it's a little bit more sterically hindered, right, than this structure here, number 4, right? This is the Z product, this is the E product, and the antigen product is definitely, I think, a little bit less sterically hindered, because you have the benzene ring and the methyl group on different sides. The Z product has the benzene ring. Oops, I don't know why I did that. Benzene ring and the benzene ring and the methyl group on the same side. So, I mean, to me, it's not that big of a big difference, right? So I don't want to make a stupid distinction between that. So I would have accepted an answer of 3 and 4, right? Or even accepted that answer there. And that's why it can be C or D, right? And so this is one of the questions also that I gave back your points for a part of the 16 points. Okay, next question here is what is the predicted major product of the thing below, of the reaction below? So this is a prime example of a bulky base. Okay, bulky base. And if you were to use this bulky base, you wouldn't get the ZZEV product as the major product. You would get the Hoffman product, because it would come over here and pull off a proton from the least substituted carbon, right? One of those protons. So that means then is that your product is going to be an alkene that's on the outside, right? Something that looks like this. Okay, and the only one that looks like that is structure 4. This one. Okay, that one's pretty straightforward. What is the predicted curved arrow mechanism for the reaction below? And then this might be the other one that had a really weird thing going on. Oh, this was a grading error, I think. Yeah, I think this one was one of the grading errors. For some reason, let's just go through each one of these and show you why each is wrong. Number one. So it can't be this first one here, and the reason why it can't be this first one here is because when you get to the second structure, you have not a positive HBr, but you have an HBr there with a negative charge. How's there an HBr there with a negative charge when you lost that proton already to the alcohol to make that water up there, right? To say nothing of the fact that this bromide is here doing an attack on this carbon for no reason at all. There's no reason why you can attack that carbon. So that's why that's not right. And then in structure 3, for some reason the water is attacking the bromine. So that's totally wrong too. So the only answer that's correct here is actually structure 2. Okay? Structure 2 is the only one that's correct. And the interesting thing is that when Blackboard graded it, it said that structure 1 was the correct one, and structure 1 is not the correct one. It is actually structure 2, so the answer here should be A. Sorry, I just did it wrong. Blackboard said that the answer should be A, but it's not A. The answer should be B, right? Structure 2. Or, reaction mechanism 2. And then, last but not least, based upon the following energy diagram, is this an E1 or E2 elimination? This is pretty easy because if you remember, E2 eliminations they're all concerted mechanisms. And what does that mean? That means that the mechanism only has one step, right? Nucleophile attacks and you lose a leaving group, for example, or you just lose a leaving group. Whereas an E1 has multiple steps, right? So I don't know what I wrote there. I was trying to spell out multiple. There we go, multiple steps. Right? Yeah, so in E2, right, is concerted. You have that, I think I said it wrong a second. I think I just told you what a substitution reaction was. What an E2 reaction, right, is when you have a base, pulls off a proton, makes a double bond, and then you lose a leaving group, right? Whereas here, so that's all one step. Whereas in E1, that's multiple steps, right? Because you have to lose the leaving group first, and then you have to do all this other stuff, and then you might even have a proton transfer. You might have you might even have a carbocation rearrangement, right? Hydride or methide shift. So this, since it has multiple steps, multiple transition states, and multiple intermediates, it's going to be E1 is the answer there. Okay, so that ends that test. Just one more time, just to make sure everybody's clear, you're going to get a 16-point curve on this exam, and that everybody will get a 16-point curve no matter what, and that's because of a number of ambiguous questions and a couple of incorrect rating. So if you have any questions, let me know, and I'll see you in the next lecture.